In this lecture, we will briefly discuss about the topic unfolding graphs in RNN. First, we should know what is unfolding in RNN and why it is necessary to learn. So, the unfolding graphs in RNN means the opening up the repeated loop of a recurrent neural network so that we can clearly see what happens at each time step. Normally, an RNN looks like one block connected to itself, which feels confusing. When we unfold it, we draw the same block again and again, and one for each time step, showing how the output of the previous step becomes the input to the next step. This make it easy for us to understand how RNN remembers past information and processes sequences like sentences or signals step by step and learns patterns over time during training. I'll tell you one practical example for this. Think of unfolding graphs in RNN like reading a sentence word by word. One sentence will take word by word if you're reading. When we read a sentence, we don't understand it all at once. We read the first word, remember it, then move to the second word while keeping the meaning of the first in our mind, and so on. If we draw this process, each word gets its own step, but our brain is the same at every step. Unfolding an RNN works exactly like this. The same network is repeated for each time step, and the memory from the previous step is carried forward. This unfolded view helps us clearly see how fast words influence our understanding of the current world, just like how RNNs learn from sequences over time. We'll see one by one. So, first, unfolding. Generally, what is unfolding graphs in RNN? The RNN processes sequential data with the memory across time steps. That means recurring neural networks, RNNs, are designed to handle sequential data by maintaining a hidden state that carries information from one time step to the next. This memory mechanism allows the network to learn dependencies in data where the order of inputs is important, such as time series signals, text sequences, or biomedical signals like ECG, etc. Unfolding converts the cyclic graph into the linear time sequences. This means in its original form, RNN contains a cyclic connections that represent feedback loops. Cyclic means what? Feedback loops. Unfolding expands the cyclic structure across the multiple time steps, converting it into a linear chain of identical network copies. Each copy represents the network at a specific time instant, and it enables the visualization, training, and backpropagation. By converting the cyclic graph into linear structure, unfolding makes it easier to visualize how information flows through time. This transformation also enables the application of standard training algorithms such as backpropagation through time, making learning computationally feasible. And if you are taking the example, ECG signal processing, where each heartbeat is processed, how we are processing? Sequentially, we are processing. Next, why unfolding is needed? First, the folded ordinance have loops that are hard to train. That means in the folded representation, feedback loops obscure how error propagates over time. These loops make gradient computation complex and unstable, especially for long sequences, which can lead to vanishing or exploiting gradients. And unfolding separates the computations across time steps. This means unfolding explicitly separates each time step into an individual computational unit. This separation clarifies how inputs, hidden states, and outputs evolved sequentially and allowing systematic computation of forward and backward passes. Next, it supports back propagation through time. Here E it should come. TIME, time, BPTT. The back propagation through time requires the network. I'll correct it. Propagation through time. This means backpropagation through time means it enables, it requires the network to be unfolded so that errors can be propagated backward through each time step. This ensures that weight updates across temporal dependence present in the sequence. The example for this case is the predicting the future stock prices using previous day prices. Today, one prices will go up, and if by considering the yesterday's price, we are going to predict the tomorrow's price. This is the so in this case we can refer this unfolding why it is necessary. Next, folded RNN representation. Here the hidden state depends on previous hidden state. In a folded RNN, the hidden state at a time. So here at a time a t, so it depends on what? It depends on the previous state. So the present state is t and the previous state is t minus 1. So in a folded RNN, the hidden state at time t depends directly on the hidden state at time t minus 1. This dependency allows the network to retain information from the past inputs. This represents forming the basis of temporal memory. Next, self loops represents the memory. This means the self loops in the folded diagram indicates that the network feeds its own output back into itself. The loop is a compact way to represent memory but does not clearly show how information propagates across the time. Next, temporal flow is hidden in the compact representation. It means although efficient, the compact folded views hides the step-by-step temporal flow of data. This makes it difficult to analyze long-term dependencies and training dynamics. So the real-time example is the real-time language modeling, where current word prediction depends on the previous words. Next, unfolded the RNN structure generally, theoretically, if you look into, each time step is represented as a separate layer. So you know that in the neural network, we have input layer, hidden layer, and the output layer. It may be having many neurons, depends on the application. So in the unfolded representation, each time step is shown as a distinct layer with its own inputs and hidden state. This makes temporal progression explicit and easy to interpret. All layers share the second point, all layers share the same weight matrices. Despite being shown as separate layers, and all unfolded units use the same weights. This parameter sharing ensures consistent learning across all time steps and reduces model complexity. And it shows explicit flow of information over time. That means unfolding clearly shows how information flows from earlier to later time steps through hidden states, making temporal dependencies visually and mathematically explicit. Say, for example, sentence. If I take I love AI, unfolded across three time steps. I love AI. Steps for word predictions. Next, time step input processing. Input at each. Here, the input time step is given by xt. Each time step receives a new input vector representing the current element in sequence, such as word, sensor reading, or ECG sample. And hidden state carries the previous information. Here, T means this will consider the T minus 1, T minus 1 previous state. The hidden states from the previous time step acts as memory, carrying contextual information forward so that past inputs influence current processing. And the network processes input sequentially. Means the RNN processes inputs one time step at a time in a sequential manner, ensuring that order and temporal structure are preserved. The example is temperature readings each hour used to predict the next hour's temperature. If I am taking 11 o'clock, what is the temperature? I can able to predict what about the 12 o'clock and 1 o'clock. So this is the best example for this case. Next, hidden state concept. Hidden state stores temporal information, means the memory. That means the hidden state functions as the internal memory of the RNN and storing learned information about previous inputs that is relevant for future predictions. And the past forward to the next step, time steps. That means at each step the hidden state is updated and passed to the next time step, enabling continuity of information across the sequence. And it captures the sequence patterns in data. Through repeated updates, the hidden states learns temporal patterns such as trends, cycles, or rhythms present in sequential data. And the example is in ECG, hidden state stores previous heartbeat patterns to predict the next beat. Next, hidden state equation, it is given by HT is equal to the hidden state computations equation is given by the HT is equal to f of WH into HT minus 1 plus WX into XT plus B. This is the input, this is the weight value. You know that H of T minus 1 is the previous hidden state, XT is the current input, and WH and WX are the weights, and B is the bias. And F is this is the activation function. Depending on the application, we are going to take the activation function. In this case, we may be considering tan H functions. The example for this is predicting the next ECG amplitude using the past heartbeat values. Next, how we are going to compute the output computation is the output is derived from the hidden state. The hidden state acts as the compact representation of relevant past and present information from which the output is computed, and it can generate the output at each step or only a final step. Depending on the application, the RNN may produce outputs at every time step. That is a single signal prediction or only at the final step. And the best example is the sentiment analysis. The example for this case is predicting the next word in a sentence based on the previous word, based on the slang or everything. The output equation is given by y of t is equal to g of wi into ht plus c. So this equation maps the hidden state to the output state, and here ht is the hidden state, wi is the output weight, and c is the bias, and g is the activation function. This may be a linear or a softmax function. So the activation function here, this g represents the activation function. It determines the nature of the output, such as linear activation for regression or softmax for classification. Example is predicting the next ECG value for heart monitoring. And how we are going to share the weight in this case? Weight sharing, the same weight across all time steps, means WH. The all unfolded time steps use identical weights and biases, ensuring uniform processing for the of the sequences. Here, that is WH, WX, WI, B, comma C. It uses the same time steps, and it reduces the number of parameters. That means weight sharing significantly reduces the total number of parameters, making the model efficient and less prone to overfitting. And it ensures consistency across sequences. That means using the same parameter ensures that the same temporal patterns are learned regardless of the sequences. The example is same RNN model predicts the ECG signal at a different heartbeat cycles. Next, learning temporal dependencies. So in this case, what you're going to learn, this is the hidden states allows the network to remember the past inputs. The hidden state allows the network to retain important past information that influences future predictions. And next, past input influences future outputs. That means the hidden states, the past input influences the future outputs. Next, it is essential for sequential data predictions. For the second point, what it says is past influence future outputs. Earlier elements in the sequence affects the later outputs, enabling modeling of cause-effect relationship over time essential for sequential data prediction. This capability is important for applications such as speech recognition, ECG analysis, and language modeling. The example is predicting rainfall tomorrow based on previous week's measurement, just for understanding. Next, back propagation through time, BPTT, back propagation through time. Errors propagate backward through unfolded steps. The first point. In BPDT, errors from later time steps are propagated backward to earlier steps through unfolded network. And it is cumulative gradient. The computation is found out by the formula dou L total divided by dou W is equal to summation T is equal to 1 to T dou LT divided by dou T. It ensuring from the entire sequence, and it enables the temporal learning. This method allows the network to learn how early inputs affect the later outcomes. And the example for this case is correcting the ECG prediction error over multiple heartbeats to improve the accuracy. So if you are taking one live example, for this case, ECG signal prediction. And ECG samples will take as a sequence of inputs x1, x2, the samples x1, x2, and xt are the samples of the inputs we are going to consider. So in this case, hidden states stores the heartbeat patterns. The hidden state captures the rhythmic patterns such as PQRST complexes and the prediction of the next ECG values. How we are going to predict the next ECG values? The output predicts the next ECG signal value, enabling the real-time monitoring. So output predicts the next ECG symbol. This is given by this that is formula y of t, symbol y of t. So it predicts the next QRS complex amplitude in a continuous ECG waveform. And the applications advantages of biomedical signals. This may be having main advantages in the biomedical signal. It provides the interoperability for sequential signals. So what do you mean by this interpretability? Unfolding makes it easier to understand how physiological signal evolved over time, and it influences the past sample. It influences earlier sample means the past samples. Earlier signal values directly affect the future predictions, aiding diagnosis, and it supports real-time monitoring. This is especially useful for the third point, useful for detecting abnormalities such as arrhythmia, and the detecting the arrhythmia by analyzing deviation from the predicted ECG values. Coming into the conclusion, the unfolding converts the cyclic RNN into linear time expanded models. Transformation of cyclic to linear structure, and unfolding converts a cyclic RNN, what it should do, RNN into a linear time expanded symbols, and it simplifies training and visualization. This transformation enables effective training and clearer understanding and wide applicability. And unfolded, so the widely used in ECG, speech, text, and sensor data analysis. And the example for so unfolded RNN are widely used in ECG, speech, text, and sensor data analysis. So the real-time example is the real-time ECG monitoring system and predicting using the next heartbeat for early warning. This is the best example for this case. Hope everyone understood the basic concepts of the unfolding of an RNN. The remaining things we'll discuss in the next lecture. Thank you.